So I was saying thanks for the opportunity to be here today. I've enjoyed my conversations with several of you, and would enjoy following up on discussions later today or in the future. So I was told that I might have as long until 3:30, so I am going to try to get through 2, maybe even 3 projects. But depending on how we go, I think people should jump in with questions as you have them. I can cut some material if need be. So the 2 main projects that I want to talk about, the first one is work that we've been doing in our group with New York City, going back to about 2008 or so, basically providing climate information to help inform decision-making in various components of New York City. And most of what I talk about there is going to be climate assessment post-Hurricane Sandy. What was a bit of New York City's experience during Sandy, and how did the city sort of mobilize a group of scientists for rapid response, rapid assessment, scientific assessment, basically. And in the process of talking about that, we can talk about some of the advantages and potentially pitfalls of sort of rapid assessment, which I think is coming more and more to climate science, whether we like it or not. Then the second main project I want to talk about is, and one thing about that first work, I will spend a fair amount of time talking about some of the decisions that we had to make in a rapid sort of context. Should we use CMIP 5 model? Should we use CMIP 3? How should we downscale? Some of those types of topics that hopefully will be of interest to people. Then the second project I want to talk about is really sort of a group of activities that I've been involved in looking at sea ice in the Arctic. One study that looks at when we could go ice-free, if you will, in the Arctic based on what climate models, the latest climate models suggest. And then I'll talk a little bit about some of our work looking at how mid-latitude weather could be affected by loss of sea ice in the Arctic. I think this is a classic sort of risk management problem. Even if the odds are fairly low that we do see a really rapid drop-off, even further drop-off from what we've seen in Arctic sea ice. Even if the odds are really lower that it does lead to real changes in mid-latitude weather, I think you can still make an argument from a risk management perspective that it might be worthwhile for mid-latitude cities and other regions to sort of think about how they might deal with potential changes in some of these extreme events. And if nothing else, I think it encourages us to sort of think about the potential limitations of climate models, and when we do risk assessment, ways that we might sort of go beyond what climate models, global models, or downscaled models suggest for possible outcomes in the future. Okay. So jumping right in, this is sort of a quick overview I was going to do about some of the work in our group. I'm at the Center for Climate Systems Research at Columbia University. We're co-located with NASA's Goddard Institute for Space Studies. And I would say sort of a common theme through a lot of our work is it focuses on impacts. It could be a range of impacts, could be agriculture, could be urban. We do a lot of developing country work. A lot of work with NASA, but sort of the common theme is thinking about impacts and increasingly adaptation, as I think I'll make clear in this talk. New York City has really done a lot in the adaptation space for several years now. So the 2 projects that I'm really going to sort of focus on, the first one is based on funding primarily from NOAA's RISA program. We have a project there where we're looking at the urban corridor from Boston to Philadelphia, including New York. I'll talk about the New York piece, but it's part of a broader project with a lot of collaborators. And won't have a lot of time to get into some of this work about NASA, but I would be interested in talking with some of you later about sort of our experience in taking some of this climate science information to decision makers thinking about facilities and infrastructure issues at various centers. The Northeast Climate Science Center is a relatively new project led out of UMass. Columbia is one of 6 institutions in that consortium, focusing primarily on ecosystem issues, cultural resources, some of the things that are within the purview of Department of Interior, U.S. Geological Survey, but increasingly I would say also sort of urban agriculture, urban ecology, green infrastructure, some of these areas I think coming to the fore as we think about ecosystems in the future. Another major project that I'd love to share with folks, something called the Program of Research on Climate Change Vulnerability, Impacts, and Adaptation. That's a UNEP-funded project that was very interesting to work on because it really sort of goes against that traditional model of sort of climate science first, top down through impacts down to adaptation, and really sort of starting from the perspective of where are the sort of key societal vulnerabilities today? What are the big sort of research questions, in some sense sort of independent of climate change? And people sort of go to read this document that we wrote up here. I think one of the messages is that a lot of the sort of resilience and adaptation work can be begun sort of no matter where we go in terms of climate change. We don't need certainty about just how much warming, sea level rise we're going to get to take a lot of steps today to reduce vulnerability. Along with a Connecticut colleague, Gary Yo, co-leading the National Climate Assessment Northeast region this time around. I'd love to talk about that with folks. And there is an opportunity actually to participate in a technical input report that we're developing in support of the National Climate Assessment this time around. If folks are interested, we could talk a little bit about that. Okay, jumping into the New York City work now. Basically, as I said initially, New York City's been looking at climate risk issues for a long time, going all the way back to 1996 or so. There was a New York Academy of Sciences funded study called the Baked Apple. Some of the big assessments since that time, the Metro East Coast study of 2001 in support of the first national climate assessment. If we go back to, say, 2007 or so, New York City's subway system was already thinking about heavy rainfall events that can swamp and shut down the system. The Water Authority, the DEP in New York, very early on was engaged thinking about how their reservoirs might be affected by climate change. They've seen a big increase in turbidity, basically sediment, in those watersheds as we've had more and more heavy rain events. And as importantly, sort of at the other end of the system, in the city, a recurring problem of combined sewer overflow events, untreated stormwater running off into the watersheds. New York City, and then just going right through to some current work that I'll talk about today. So just to make the case that there's sort of a long foundation in New York City about thinking about some of these issues. So a really key event was related to Mayor Bloomberg in 2006, 2007 or so, forming Plan YC, a sustainability-oriented initiative that initially didn't really include a lot of adaptation work, focused on reducing greenhouse gas emissions and sort of quality of life green issues in the city. So pretty early on, we got to talking with some of the mayor's people in the Office of Long-Term Planning and Sustainability, really just sort of making the point that adaptation needed to be part of this equation as well, that we were locked into some additional sea level rise, warming, and really to sort of protect the city's legacy and even to protect some of those mitigation initiatives, you had to be thinking about adaptation at the same time. So the first New York City Panel on Climate Change, which was a scientific body that advised the city, formed around 2007, 2008, and included climate science, but also a lot of other different components, private sector agencies, to really sort of look at some of the city's vulnerabilities and help propose some adaptation strategies. So I want to have a slide just sort of describing how this whole process worked, because I think institutionally there are several sort of elements that were key to this sort of working so well for the city. Certainly the leadership at the highest level, Mayor Bloomberg sort of attending the sort of kickoff meeting of these groups, sent the message to all the different commissioners that this was something that was important to the administration. And as I alluded to earlier, part of that Plan YC, there was a formation of a really sort of new group called the Office of Long-Term Planning and Sustainability with very close access to the mayor. That wasn't situated in any pre-existing agency, so you didn't have a lot of sort of turf war kind of issues. It was really sort of an independent entity that all the different agencies basically had to report to. And then you see this sort of two-tiered structure in terms of this adaptation group. On the one side, the group from the last slide, the New York City Panel on Climate Change. This is the sort of expert body. As I said earlier, you have the science community, climate scientists, private sector experts too, risk management people, economists, legal experts, people from the insurance sector, providing that climate science information. But at least as important, really sort of an even bigger source of sort of information, really the stakeholder task force of city agencies, some private sector companies, CSX, Amtrak, a lot of the telecommunications providers were part of that as well. It was initially very focused on infrastructure back in that sort of first phase of our assessment work. Not a lot of consideration of vulnerable communities, not a lot of consideration of public health, ecosystems initially, a very sort of technocratic approach, you might say, with these infrastructure work groups are centered around energy, transportation, a policy group there was, and then sort of water and waste, sanitation issues, and communications. Each of those groups had a sort of very unique threat, a very unique set of vulnerabilities, different time frames that they thought about. If you talk to people in the communications sector, as a rule, the telecommunications companies, the story tends to be if it's further than 10 or 15 years out, not a big concern for us because we're engaged in such sort of intense competition with other cell phone providers. The technology is changing so fast, we probably don't need to think a lot about what's happening sort of 15 years from now. On the other hand, on the transportation side, if you're talking to Metropolitan Transit Authority, they're thinking about bridges, things like that, there you have a 100-year time frame, lots of really valuable assets. Port Authority in charge of the airports, they absolutely care about 100-year projections. They want to know a worst-case scenario for sea level rise. So depending on the group you're talking to, a very different set of questions. One group might be more likely to focus on sort of a worst-case scenario in the distribution. So it was sort of, but a key part of this work was that the scientific body met frequently with this group, asked, what are the things you worry about today? What are the ways that your system is impacted by weather today? That was sort of the starting point. What are the assets you're most worried about? What parts of your mission seem the most sort of vulnerable today? That was really sort of a starting point. Then the climate science sort of came in. That helped frame, what thresholds we looked at. Was it days over 90, days over 95? And sort of related questions. Okay, so one of the, I think sort of takeaway points of that initial assessment was to really kind of embrace the uncertainties, not just on the climate science side, on the impact side. What's going to happen to human population living in the coastal areas? Big uncertainties going out 50 years. What's going to happen to technologies? How is the vulnerability of different sectors going to change in some of these areas? Are there some adaptation strategies that today sound totally not feasible that might make sense in 40 or 50 years? Given all those uncertainties, how can you sort of build an approach that is flexible to the idea that some of these things could change? So this is obviously just a schematic, but the sort of basic idea here that there's a societal sort of level of risk that might vary, sort of how comfortable people are with risk, and that as time passes with climate change, higher sea levels, higher temperatures, our vulnerability is going to go up. I mean, you'd really probably argue that this should really sort of already start above here, but anyway, over time, you pass an unacceptable threshold of risk. Now, to some extent, if you set an inflexible adaptation policy, if you build a seawall but give it a narrow base so you can't change its height later, you do reduce your vulnerability somewhat, but it continues to sort of go up through time. So the question we were asking was, is there a way to do this adaptation piece where you sort of build in more flexibility? If you get new information, sea levels are rising higher than we thought, new adaptation strategies might be possible. Can you course correct? Can you build, the stereotypical example would be to have a broad base to your seawall there so you could change the height if new information came in. You're still eventually going to get above that risk threshold. It's still going to be untenable to live in a lot of coastal areas if you go far enough out in time based on our current understanding. But you can sort of delay that day to some extent. And of course, if you add mitigation or reduce your greenhouse gas emissions and get traction at a societal level, you can pull that risk down even further. Okay, so let's get down to some sort of more practical examples here now. What had New York City sort of done before Hurricane Sandy, partly as a result of this assessment work, but obviously for a lot of other reasons too. There definitely was a program well underway to increase green infrastructure. So you think in New York City today, all the examples you see of small parks, a lot of those green spaces that you see actually have some, somewhat complicated engineering underneath them to catch and store water as well. Efforts to prevent so much stormwater runoff were underway. Cities also was taking steps to get more detailed information about some of the heights of various parts of the topography. Sea level rise was being built into the waterfront plan that the city was developing, and the Office of Long-Term Emergency Management had begun to sort of take some of that information into their sort of pre-storm preparations, for example. So then Hurricane Sandy, of course, came along, and these are going to be things everybody's probably very familiar with, but some of the things that were so unique about Sandy, the fact that for parts of New York City, it hit right at about high tide. and then it was a higher tide than normal, of course. What's interesting to note is that this wasn't high tide for the whole city. I mean, one of the things that sort of emerged a few months later was the idea that in some ways it could have been worse. In some ways, if the storm had hit several hours later, as it was sort of the worst case for the battery, and where some of the key, what we think of as sort of the economic assets, were also parts of the South Shore of the city. But for some other areas, like some of the food distribution centers in the Bronx, so really sort of critical food distribution center, the storm actually did not hit at high tide. So it could have, it could have been a worse case if it had gone a little differently for some other parts of the city. Certainly the size of the storm was remarkable, and that obviously a critical part of determining why that surge was so big, so much more than we think of for that level of wind or that level of central pressure, and also the fact that the surge was over such a big area. And then, one piece we can talk a little bit about was that unusual storm track as well. There's a paper by Hall and Sobel suggesting that an angle like that storm took along the Jersey Shore might happen roughly once every 700 years. Obviously, big error bars on that estimate, but an unusual track to some extent. So in terms of the city's immediate preparations, there was a mandatory evacuation of many areas. Not all the areas that should have been evacuated, as it turned out, but many areas. The subway system was, of course, closed down. There were a lot of out-of-state crews brought in before the storm. These are some of the things that helped get things up and running faster, but clearly a lot went wrong. At least 43 people died within the city itself. Those estimates vary. 4 to 8 million people, you sometimes hear, left without power in the region, and 7 subway lines, many tunnels shut down for a week or so. Some of these impacts, as I alluded to earlier, had been forecast in advance to some extent. If you go back to that 2001 study, it had graphics in it showing the elevation of the airports, showing the elevations of some of these water tunnels, and showing what a little bit of sea level rise, plus storm surge would mean for those assets. And then I don't know if people can make out some of these images here. Damage at the South Ferry subway station. That subway station alone suffered roughly $500 million in damage from Sandy. It was like a flagship station. They had just rebuilt it, new signals and such. And then sort of at the other extreme, that's the sort of high-tech example, then you had the sort of coast along Rockaways where you see this entire set of boardwalk torn away, and then the extensive power outages I mentioned earlier. So what were some of the unforeseen or maybe less predicted or less understood impacts? Certainly one of the things that got a lot of attention during and after the storm, the vulnerability of the hospitals. A lot of the services were right along Manhattan, for example, right along the water. A lot of the hospitals flooded. Was there an ability to get people out safely? Certainly there were some issues there. I think certainly this question of the gas shortages, complicated problem. I mean, to some extent it was an issue of flooding at some of the distribution centers west of the city, southwest of the city, partly just a simple issue of the electricity being out. It was made it impossible to pump gas in some of these stations. That's a problem that obviously persisted for weeks. And then fires. To what extent were some of those fires that we saw that, of course, were so hard to manage given the fact that there was storm surge and wind at the same time, but were some of those fires actually caused by combination of salt water, running into batteries and things like that. So those are, I think, some of the impact assessment things that we're thinking about now. So what are some of the links to climate science and climate change to Hurricane Sandy? Really, there's only one clear and sort of undeniable link. And that's, of course, the issue of sea level rise. Our region has had roughly a foot of sea level rise since 1900, 7 or 8 inches of that, consistent with global sea level change over that time. The other 3, 4 inches, glacial isostatic adjustment, not related in any way really to the increases in greenhouse gases since the Industrial Revolution. But the point is really that what sounds like not much sea level rise, just 8 inches or so, already is enough to shift the probability of coastal flooding in a significant way. That's one of the real take-home messages. And I'll show that when we get to the projections even more. So more frequent coastal flooding, and then of course that 8 inches made a difference in some places. It was additional homes flooded and deeper water as well wherever it occurred. So obviously the two much trickier links to make, the link to storm strength itself. Was Sandy made any stronger by climate change? We certainly don't have enough evidence to suggest that at this time. And what we can say that the upper ocean temperatures have gone up by something like 1 degree Fahrenheit. Certainly some of Sandy's track took it through waters that were a lot warmer than that, primarily anomalies much greater than that, largely just due to natural variability. But before we try to link Sandy or cyclones to climate change, we've got to think about all the other factors as well. What's happening to wind shear? What's happening to dust? What's happening to the stability of the atmosphere? So that's obviously a very, very tricky one. And then I think at least as tricky is some of the research that'll tie into what I talk about in the second half of the talk. There has been this body of research that we've been involved in, pointing to the idea of loss of sea ice in the Arctic, being consistent with a weaker jet stream, a wavier jet stream. All things being equal, that can make it easier for storms to make a track towards the west. How do you link that to Sandy? We're talking about one storm. You really can't link it to Sandy. But I think from a risk management perspective, it's worth investigating in models and as we pick up more observations, whether we do see more of this type of sort of wavy jet setup with loss of sea ice in the Arctic, and potentially more of a variety of types of extreme events. But for now, purely speculative, I think, in the case of Sandy, to try to link it to anything to do with sea ice. Although there have been a couple papers, one in oceanography, that did explore that possibility. Okay, so now let's turn to New York City's effort to sort of engage with New York City panel on climate change post-Sandy. Actually, a little before the storm hit, the New York City panel on climate change was codified into local law as part of the charter for New York City, that even if the administration changes, when the administration changes, the city should every 4 or 5 years sort of revisit, roughly consistent with the new IPCC reports, the climate science. Everything from the projections to sort of improved physical understanding, growing observational record, for example, some of the justifications for that. Now, after Sandy, the city reconvened the New York City Panel on Climate Change, January 2013, to support this special initiative on rebuilding and resilience. And we basically had about 3 months to do a whole new set of projections. One of the first things we said when we engaged with the city was, the way the science works is the projections aren't really going to change much. It's basically probably going to be very similar to what we released 3 or 4 years ago. But the really sort of clear message from the city was, that's fine. We need to find out. Even if that ends up being the answer, that's okay. And a related point, I think, just sort of the optics being, the city wanted to be able to say that they had gone to the CMIP-5 models. They had sort of reconsulted the science. And so you end up in this sort of interesting case where, there's sometimes a feeling in as a climate scientist sort of working with decision makers, you're sort of working on very important questions with a lot of applied value, but sometimes it doesn't feel like it sort of advances the science or the publications. I think this was a very interesting case where the city really sort of pushing us to do this work with the CMIP-5 models actually pushed us to do work we would have done anyway on a faster time scale and really sort of helped us from a research perspective. So it's sort of an interesting case of a stakeholder decision maker actually moving the climate science forward, the sort of assessment using the latest models. So to quickly sort of overview some of the findings of our report released in June, very similar, as I said, to the suggestion from 2009, acceleration of some of the changes that we had observed over the 20th century, focused on New York City, but obviously a lot of the projections extend out to a much bigger area as well. And we'll go through some of these findings in the next few slides. So a quick sort of overview of trends for the region. New Haven's values would be pretty similar for a lot of these variables. New York City's actually had over 4 degrees of warming between 1900 and 2011, far exceeding the broader regional trends, which are somewhere around sort of 2 to 3 degrees Fahrenheit since 1900, roughly, depending on where you are. There has been an uptick, upward trend in precipitation. In general, if you compare that increase to natural variability, the trend is pretty small, certainly not anywhere you'd want to start in terms of projections for the future. The variability sort of continues to be the story, not the trend on precipitation, especially when you go to such a fine scale as city scale. These are annual precipitation. And some people have sort of noted that it looks like the variability increases a lot in the second half of that record. But I wouldn't put too much credence on that either in terms of linking it to any climate change signal. Of course, the exception is the sea level rise story. There, as I said earlier, as with all these variables, you have that year-to-year variability, but clearly, from a risk management perspective, for a long time, we've been in a state where the trend has emerged relative to the earlier signal. While there's year-to-year variability from a risk management perspective, clearly we've already picked up actionable information that can help inform decision-making relative to, basically another way to say that is just the years with the low sea level today are still a lot higher than the years with the high sea level were in the past. So huge uncertainties, but from a risk management perspective, at what point is there a signal beginning to emerge that can be used in risk management? For extreme events, we don't really even try to do trends or to attach significance to trends at the city scale. It's a risky thing to do. Over the broader Northeast, we've seen about a 75% increase in the heaviest rain events, the sort of 1% rainfall events. That's over a big area. That's over roughly a sixth of the country. And we were just talking about this during lunch. There has been a tendency for a little more strong hurricanes over the last 2-3 decades. Science is really still out over whether that's going to continue in the future or not, as I said earlier. Okay, so there's sort of risk management approach that I keep alluding to. What do we mean by that? We used as broad a set of climate models as were available to sample that range of possible outcomes. 33 available GCMs, multiple representative concentration pathways, these assumptions about future greenhouse gas concentrations, to really sort of bound a set of possible outcomes. Not the full range of outcomes, because we know there are possibilities beyond what the climate models suggest. But the city was interested in getting some sense of sort of what these bounds were that were suggested by the models. Again, you can't call it a probability. You can call it a model-based distribution. So in terms of the methods and how we went about this assessment, we focused on the mean annual changes, what's going to happen to average sea level, average temperature, average rainfall, but also some of these extreme event thresholds that the city and stakeholders consistently asked about. Days over 90 degrees. Important from the energy sector perspective, from the public health perspective. Days below freezing, a big issue for transportation sector, obviously heating as well. And then, as I said earlier, use 35 global climate models, 2 of the representative concentration pathways. This roughly corresponds to A1FI from the last sort of iteration. This roughly corresponds to the SRES B1. We do 30-year time slices. We're not trying at all to capture any of the year-to-year variability. We're not trying to capture 5-year variability. We're sort of focusing on whatever piece of the signal there is that's linked to greenhouse gas concentrations. That's all we're really sort of trying to get here. So a 2020's time slice is defined as 2010 to 2039. Think of it like a climate normal with increasing greenhouse gases. Our approach was just to use one ensemble member per GCM this time around. A lot of the GCMs, several of them have many different ensemble members. We've done prior work that suggests as long as you're doing sort of 30-year averaging, it tends not to make much difference whether you use one ensemble member or many. And we take a very simple approach to the downscaling. A lot of people wouldn't even call it downscaling. We start at the GCM resolution and just use the single grid box that corresponds to New York City, and then just take an approach to calculate the extreme events known as the delta method, where basically all you're doing is for a given calendar month, like January, go to any one of these climate models, and for this 30-year period that I called the 2050s, for example, 2040 to 2069, figure out the average temperature over that 30-year period for all the Januaries. Compare it to the 30-year baseline temperature for that same GCM over a hindcast period, roughly 1970 to 2000, and just apply that change factor for January to the historical daily data for New York City, Tmax, Tmin at the daily scale. This type of approach does not capture potential changes in interannual variability. It doesn't capture changes in the variance within a month. So it's a limited approach, but of course, if you go to those issues related to variability, the first question you come up with is how much confidence do we have about that? This approach is based on the assumption that changes in the mean are more reliable than changes in the extremes or changes in the distribution. It's a debatable assumption. There's research on that, but that's the approach used here.
Given New York's situated on the coastline, is there any issue using just a single grid box to downscale?
Yeah, so we actually would take, a lot of times it ends up being a grid box that's a little to the northwest of the city. But if we compare the change factors over any of the land-based grid boxes for these 30-year averages, they're going to be about the same in this region. If you're in a really mountainous area, it's different. If you use a water-based grid box, the changes, especially for temperature, can be a little bit smaller. So we intentionally grab sort of the nearest one that's like fully over land. Another approach is just to regrid everything, and then that's not what we did here. So we can talk a little maybe in discussions later about alternate approaches here. What would happen if you used regional climate models, the NARCAP simulations? Those are at 50-kilometer resolution. Of course, there, the issue you run up against with regional climate models is basically computational expense. How do you get a combination of true improvement in spatial resolution with a long time scale? The NARCAP simulations at 50 kilometers are only available for the 2050s time period. You can't do other time slices. They're only available for one emission scenario, so you can't sample that potential range of future greenhouse gas concentrations. And I think sort of the biggest issue in terms of what they're sampling is they tend to be run with only a couple of these GCMs. So you're really, in trying to get a little bit better fine scale resolution, you're sacrificing a lot in terms of your large-scale boundary conditions. So those are some of the issues related to RCM. Certainly there are others. There are statistical downscaling approaches that could be used as well. We've sort of taken the approach here with New York City of, I mentioned all the agencies before. They want a sort of unified, kind of quick approach that the whole city can use. But if you're sitting in DEP and you're thinking about the reservoirs, you're thinking about snow cover in the Catskills, that's the type of application where you might want to look at a statistical downscaling approach that links historical relationships between snow cover in the mountains with large-scale features that a climate model might do well. Regional climate models have been used in higher elevation parts of the Pacific Northwest, for example. But I think, this Horton et al. 2011 paper, we showed that for the type of questions that New York City was asking, regional climate models and statistical downscaling didn't give a lot of value, didn't lead to very different results at all. Okay, so just sort of a quick take on these projections now. So when we have 35 different GCMs, 2 representative concentration pathways, you get a sample of basically 70 possible outcomes. The city asked us for these points in the distribution, basically. So the 10th percentile means roughly 7 of the 70 models had less than 1.5 degree Fahrenheit of warming by the 2020s relative to this 1970 to 2010 base period. Central range, sort of half the values, falls between 2 and 2.8. You can do the same thing for precipitation. In general, over the northeast, and actually even more so over the southeast, the CMIP-5 models seem to be suggesting a little more precipitation than the CMIP-3 models did in the future. It's not a strong signal, but in general, there's a few more models, especially over the southeast, showing increasing precip, including in summer, relative to what we saw with CMIP-3. But still, at the end of the day, the year-to-year variability with precipitation is going to be a lot bigger than the kind of numbers that we're seeing here. Okay, so what happens when we look at extremes? And again, this is just that delta method-based approach. We're not looking at how the distribution of extremes could change. We're not looking dynamically at whether there's going to be more sort of blocking high-pressure systems at a sub-monthly scale. This is just the sort of shift in the averages. Sorry, didn't go to it yet. Okay, so just picking a couple of these threshold extremes, days over 90. Over the 1970 to 2000 base period, New York City averaged about 18 days 90 or above. So just a small shift in the average by the 2020s. This is that 10th percentile, that 1.5 degrees or so of warming. If you apply that universally to all the historical daily Tmax data, you go up to 24. So you can see, even just out to the 2020s, you're already getting, under the worst case scenario, roughly doubling of that frequency of days over 90. Of course, it's also the duration of the heat waves that would be expected to increase, the magnitude of the heat waves. And even just out to the 2050s, sort of mid-range scenario, giving you something like 2.5 times as many days over 90. So it's really hard to imagine a situation where even that small shift in the average could not lead to a significant increase in the number of days over 90. You need a total redistribution of circulation to not see a big increase in these days over 90. And this is something that New York City, New Haven, I'm sure as well, extremely vulnerable to today. A lot of these really warm days are days where air quality tends to be poor. We have a greater probability of the power going out. Just a couple extra degrees makes a lot of difference at the high end. It's not all a negative story, of course. The frequency of days below freezing, by definition, by this method, has to go down. You see something like a 33%, 30% drop or so in days below freezing by the 2050s with this approach. Okay, so let me say a little bit about the approach we took to the sea level rise projections now. This is sort of the classic case where you're sort of limited in how much you really can rely on climate models. What we tried to do here is use the latest CMIP-5 models for those components of sea level rise that you can go to the models for, but also to bring in as many other components as possible. As one of the first efforts to look at 6 different sea level rise components for a very sort of hyper-local city level projection, and again, using the latest climate models where possible. So here you had about 24 GCMs that were available for these 2 terms, one of them being basically the thermal expansion, the global average increase in ocean height as it warms. And the second component, the relative ocean height, the idea here that ocean height isn't constant. There's a tendency right now for the waters along the northeast coast to be significantly lower than the global ocean average. Some of the climate models suggest that as we get out into the future, if we get a freshening of the North Atlantic, maybe partly due to more ice melt as well, increase in that freshening, maybe a weakening of the Gulf Stream, which all things being equal would tend to pull up the waters along the northeast coast. That's part of why some of the literature, Yin et al., Salinger et al., has suggested that we could see greater sea level rise in the northeast than in other areas. Additional component is the fact that we have some land subsidence of something like 3 inches per century over most of the northeast. Okay, but what are some of these other terms that are more challenging? Certainly the elephant in the room is always this meltwater term. What's going to happen to the land-based ice sheets, Greenland, the 2 components of Antarctica, and to a lesser extent, the mountains and glaciers. So we can maybe go into that a little later if we have time, what we did there. But we basically primarily just went to an expert elicitation by Bamber and Aspinall that really sort of tried to bring together a bunch of different components. We know you can't use GCMs to get these terms, so we went to this expert elicitation. The land subsidence term, very straightforward. Just as I say, 3 to 4 inches for the region. For the first time, we looked at the land water storage. This brings in a whole different set of assumptions. What's going to happen to dam building in the future? What's going to happen to extraction of groundwater? There's a lot of different ways you could go on this, but the bottom line is it doesn't affect the results much at all. You're talking about sort of 1 to 2 inches of sea level rise difference, depending on which scenario you go with. And then for the first time, so these were sort of components that we didn't look at the last time around. This time, we also looked at what's called the fingerprint term. The dominant, this is basically the idea that depending on where you lose that ice, you see different effects at various points in the ocean. And sort of the iconic example of this is if you got sort of let's say 1 meter equivalent of sea level rise by melting ice sheets. If all that melt happened in Greenland and none of it were to happen in Antarctica, our region, New York, New Haven, would only get about half the global average sea level. So we get like 1.5 feet if the global average increase was 1 meter. And that's primarily, almost exclusively a function of the fact that if you're losing that mass from Greenland, there's less of a gravitational pull. The water essentially sort of moves away. All right, so our projections based on all 6 of those components out to the 2050s or so give us under that worst case scenario, which interestingly is the one that New York City's been really designing to and focusing on, somewhere around 2.5 feet of sea level rise by the 2050s. We're in the process of extending this now out to the 2080s and 2100. It looks like, as with the last time we did these projections, we're going to be somewhere in the sort of 5-foot ballpark probably by 2100 or so. And I think based on the precautionary principle and these long-term infrastructure assets, as I said earlier, the city has been focusing on the sort of upper end of these estimates. So what does that shift in the average sea level imply for the frequency of coastal flooding, independent of what might happen to storms? We don't know how hurricane frequency is going to change. We don't know how nor'easters are going to change in the future. What does that increase in sort of baseline sea level alone imply for the frequency of coastal flooding? That on the next slide here. Okay, so under that scenario for the 2050s, what's defined as the 1 in 100-year flood today, the flood that happens 1% probability in any given year, just by virtue of that 2.5 feet of sea level rise by the 2050s, becomes something that happens 5 times as often. without invoking any stronger storms, very large increase in the frequency of coastal flooding. And of course, simultaneous with that, the actual height of the floods goes up as well. So more frequent and more damaging when they happen without invoking any change in storms themselves. If we depict this visually, these are the updated flood maps for the city. The baseline flood risk shown in purple. As we get out to the 2020s, under an 11-inch sea level rise scenario, the additional areas in yellow flooding. And by the 2050s, the red flooding at 31 inches. So you see there's a big difference throughout the city. Some areas, the sea level rise doesn't have a big impact on the amount of additional flooded areas, but areas where you have flatter coastline, essentially, big increases in the amount of flooded area. And for what it's worth, the 1 in 100-year flood zone, that obviously deserves a lot less credence even than the 1 in 100. It's important to understand as we look at these are not well-known quantities, the 1 in 100-year coastal flood. This is as much sort of a regulatory tool, I would say, as a sort of well-known thing, given go ahead.
I'm just looking at this and I'm wondering if FEMA has a similar process of like consulting scientists and updating their maps, and if they coordinate with New York about which projections.
So I think that issues of transparency in FEMA's process have sort of really moved to the fore to such an extent. I mean, that's I'd say the question that everybody's asking. And I think more information has gotten out about the process. I don't know a lot about it, but historically it hasn't always been clear the ways that FEMA has done that. But this is actually showing FEMA's initial updated estimates. So there's really two things going on here, actually. The last set of FEMA estimates of the 1 in 100-year coastal flooding. So we're not talking about the sea level rise yet, just this sort of baseline piece here. The last time that was done was in the early 1980s. And when that was, it's basically being redone right now, and these are sort of preliminary estimates. That factor alone, separate from anything to do with sea level rise, is going to lead to roughly a doubling of the number of properties and people in New York City that are estimated to be 1 in the 100-year flood zone. When we go to the 2050s, 31-inch sea level rise scenario, you basically double it again. So if you were sitting, 5 years or so ago with the 1 in 100-year coastal flood maps that existed then, if you weren't considering sea level rise, you'd say there are about 200,000 people in New York City in the 1 in 100-year coastal flood zone. Today, based on the sort of current estimate, now these could change, they're preliminary. They'll change over the next couple of years. But with sea level rise and with those new estimates of the 1 in 100-year flood risk, the number's gone up to 800,000. So I mean, it's interesting. The city is definitely considering that worst case scenario, and we can talk a little bit about what some of the reasons for that are, because I think it's an interesting question. But certainly not something we expect to see everywhere, the sort of embracing of worst case scenarios for, I shouldn't call it a worst case scenario, but a sort of more extreme outcomes. All right, so summarizing the sort of New York City piece of this now. So our report was just a sort of 50-page climate piece, but there was a much larger, something like 450-page assessment done by the city itself that our work just fed into that really did look at some of these issues. How many buildings are vulnerable? Focused on some of the most vulnerable communities. And I have a link, again, one of the first couple slides is actually a link to this report on my second slide, which hopefully everyone can get later. And then some of the recommendations, basically a lot of focus obviously on the coastal flood and Sandy risk, but the city I think acknowledged that heat waves remain one of the biggest vulnerabilities for urban populations especially. Heavy rain events have inundated the system in the past and will again in the future. So as these adaptation strategies are developed, there's an estimated $20 billion in damage from Sandy. There's a $20 billion resilience plan. It's very focused. It's focused on a range of strategies: green infrastructure, elevating buildings, even some sort of flood barriers for sort of local communities. One thing that is not prominent in it is discussion of retreat from the coast. So I think that's something that I'd love to talk about later. It's not a message that really emerges from this report, and I think that's important to think about, even if you sort of accept the premise that maybe New York City is going to be able to sort of build its way or spend its way out of some of these risks, which is a big assumption. We need to ask whether there's a danger of other regions that might look to New York for guidance getting sort of too sanguine a view of the possible outcomes. And we know there's a lot of places where there's never going to be enough money to prepare for rising sea levels of what we might experience. We know there's a lot of places where you can't build a seawall, right? The limestone examples that you hear about off the coast of Florida, where the water would just sort of percolate up from underneath. So retreat, clearly needs to be part of this discussion. All right, I'm definitely not going to be able to show any of the slides on regional climate modeling. I'm going to jump now to talk a little bit about some of the Arctic sea ice research. Would this be a good break? Should we take a little break for questions, or should I keep going and do questions at the end? The next part is a very different topic, so maybe this is a good break point.
Sure. Why don't we break, ask questions if anybody has them.
All right, that was easy. All right. Yeah, go ahead.
So when you downscale the global models, do they become useful for other neighboring cities as well? I'm curious about the kind of communication that happens between cities, either through city networks or just scientists using the same models.
So, I think my understanding is that Connecticut in 2009 or 2010 basically used our projections for that sort of first work that I think was out of the governor's office, if I'm remembering right. I may have that wrong. But basically for the mean changes, average temperature, sea level for most of this region, there might be a few places where you have rapid groundwater extraction or sediment, but for the most part in this area, there's not going to be big gradients in these sort of mean changes, sea level, temperature, precip from one of these grid boxes to the other. Now, of course, when we go to something like days over 90 degrees, it could be a very different story, depending on whether you're right along the coast or not. Heavy rain events can differ a lot. As we get sort of, there's actually a pretty significant damping of the heavy rain events as you get sort of close to the water. So days over 90 would be very different, but the percentage change in the days over 90 wouldn't necessarily be.
I was just wondering how much of, when you're doing the modeling in an urban setting and you have Manhattan versus Brooklyn and the density differences, how much does urban form play into the factors of looking at subsidence or flooding in terms of when you're looking at risk ahead and those types of infrastructure investments over the long run?
So that's just the kind of thing that I'd say the city's really getting into now. Looking at some of that, they have a big initiative now to map, for example, as we see sea level rise, are all areas going to see sort of wave inundation at exactly that sort of sea level increase in height, or will there be some nonlinearities that cause some areas to get more? What's the path that the water takes when there may already be structures, seawalls in place right now that aren't being detected? So we're definitely not there yet. I'd say a lot of the green infrastructure initiatives are sort of trying to do it. There's certainly efforts to do sort of block by block modeling, but I couldn't speak to sort of how successful those are yet. But they exist. There are definitely models being developed to sort of track how water even moves sort of under the city. From an urban heat island perspective, we're not really sort of speaking to that at all here, except insofar as we're bias correcting to Central Park's weather station. But that's a big research area. We actually have a project looking at that. The real way to do these projections would be to take this global climate change piece, but then also to think about the fact that some parts of New York City, at various times couldn't be 6 degrees Fahrenheit warmer than others. Sort of put those two together.
So you said there wasn't a lot of mention of retreat as a strategy moving forward, but what was the receptivity to talking explicitly about maybe changing the land use in those most vulnerable areas, maybe shifting residential populations out of some of those areas? Is there any more discussion of that as an intermediate?
That's a really good point. Retreat is kind of too simplistic a take. What does that mean exactly? Could something else be there, something that can flood occasionally? I think those discussions are sort of being had now. I don't think it's sort of clear what the answers are yet. And there have been, just even in the last few days, I actually have heard about a few buyouts in Staten Island. So there's maybe a little bit going on in the retreat sphere, but it's not what you're sort of hearing about every day in the initiative, I would say. But that's, I think the way I would sort of take your comment is this can be more nuanced. This is part of a sort of broader planning decisions about, it doesn't have to be sort of leave or stay necessarily.
You were showing a table of, for example, how many extra days of extreme heat that you could get with just shifting the mean.
Yeah.
I
I know that, for example, in Europe, they've done some regional modeling where
Yep.
they find support for actually change in variability
Yep.
too, so that you get wider distribution
Yep.
along with that shift in mean. So
Maybe I should show those slides quickly. I have a few things on that too. And we actually looked at the NARCAP models. Maybe I'm just going to quickly show a result there, then I'm going to get into time trouble. But yeah, I think especially on the extreme heat side, I mentioned a little bit of the work suggesting more blocking events potentially, but also soil moisture feedbacks potentially can give you a bigger increase in extreme heat. Just extremely quickly, if you look at the NARCAP RCMs, and this is an ensemble about 5 NARCAP RCMs, obviously driven by 5 GCMs. What I'm showing here is, so everything with NARCAP is the 2050s relative to a base period. Where you see red is places where the warmest, this is the min, the coldest day per year is projected to warm more than the typical winter day. So you see a pretty broad area where, based on these 5 sort of NARCAP RCMs in winter, you'd see as much as, this is Celsius, is potentially as much as 6 degrees more warming in the coldest day than in the sort of typical Tmin. So we haven't gotten very far with this yet. I mean, the next step obviously is there a plausible mechanism for this? And do these models reproduce the right type of features when you have these really cold days? So that's sort of where we are now. But here are some of the possible mechanisms that could influence changes in the extreme cold or the extreme heat. And just sort of quickly to look at the corresponding figure on the heat side. So here, where you're seeing yellows and especially reds, places where the hottest day per year in the NARCAP RCMs at this 50-kilometer native resolution are projected to warm more than the typical summer Tmax averaged across the 90 days. So, I mean, if there's anything to this result, it's a knockout for the Northeast because, as we were saying earlier, a couple extra degrees matter. But the question is, at this point, we're not really sort of confident at all that this is a real feature. But you're right. Certainly, there's been a lot of really good research out of Europe, especially on the heat side. Yeah.
I was just wondering, are other American cities going through similar assessments?
Yes. Yeah. A lot of California cities are. There's statewide efforts that are, I think, further along than New York's efforts. We've done assessments at New York State level. There have been bigger initiatives, for example, in California. LA's done this. San Francisco's done this. Chicago would be some of the examples. But yeah, there absolutely are.
And just to follow up, is any of the results of these assessments being used to encourage policy change at the federal level?
At the federal level, yeah. I mean, certainly, I think that, yeah, I mean, so there's a lot of ways to handle that one. I mean, certainly for the National Climate Assessment, there's a lot of effort to sort of elevate some of these stories coming out of the cities. I think it's sort of widely acknowledged that the cities are leading, in all this type of work, mitigation and adaptation. Yeah, so I mean, and I think we're going to hear about some new initiatives in the next couple of months too. This Bloomberg, Paulson, Steyer initiative is going to be, the kind of thing that's really going to sort of push the envelope on sort of upscaling some of these individual city results to where they sort of can't be ignored at the federal level. All right, I am going to sort of do a quick spin through some of the sea ice research now. Okay. All right, so just going to quickly talk a little bit about trying to sort of pinpoint how much of the recent loss in late summer sea ice may be due to human activity as opposed to natural variability. A little bit of projections based on the latest climate models of when we could go ice-free, and then what might some of the implications be for mid-latitude weather. I'm not going to have enough time to get through everything. So the motivation is clearly the Arctic's undergoing rapid change, not just sea ice, many other examples. Poorly understood area, lots of potential for powerful feedbacks, mostly positive, but some negative feedbacks, unique and fragile ecosystems, and obviously increasing geopolitical importance. I think there's been over 100% increase in ship traffic through the Bering region just over the last 5 years. I think I'll skip some of this sort of background information, assume everybody knows that we've seen a big decrease in September sea ice extent. Important to note, though, that 2013 showed an uptick. That's the extreme minimum, the minimum of record from last September 2012 relative to the sort of typical climatology for September over the last 30 years. September being the month when you tend to have the least sea ice. Volume has also decreased dramatically. There's where we sit in 2013. Big error bars on this, but it's looking like volume has gone up a little bit from the same point in the last few years. Sea ice thickness, 2013. And then some recent research suggesting that the sea ice extent that we've observed the last few years, the lowest for late summer in at least 1,450 years. Okay, so getting to this estimation of the sort of role of human activities. This is a plot on a paper that we're developing showing what happens if we go look at the existing CMIP-5 models when they're run in a pre-industrial simulation, sort of constant greenhouse gas concentrations. And what you're seeing here is a fraction, the ratio between the trend for all possible 33-year windows in those climate models that don't have any increase in greenhouse gases compared to the ratio of the actual trend we've observed in September sea ice extent over the last 33 years of observations. So basically, obviously a histogram, there's very few 33-year periods where even where the trend is even 30% of the size of the actual observed trend over the last 33 years. So very few examples where even a third, where the trend is even a third as big in the models over a 33-year period. So that makes it less likely that natural variability is a big player here, but it doesn't exclude the possibility because these climate models may be missing natural variability as well. That's one of the challenges, to identify the role of natural variability. Here, a similar plot where we're looking at a much shorter period, though, which is always dangerous. The 2006 to 2012 difference in sea ice extent. That was that period where we saw this big decrease in observed sea ice extent. Millions of square kilometers here. That's the observations. Now here, how many climate models over that same period, 2006 to 2012, were able to reproduce a trend and decrease as large as that we observed. So there actually are a few that do, but obviously the vast majority not showing such a large decrease. This points to the idea that it appears that the climate models are maybe undersensitive to the rate of sea ice loss in the Arctic, although again, we can't totally exclude the role of natural variability in some of that decrease. So based on some of those approaches, we tried to ask the question of when we could go down to an ice-free state, which we defined as 1.7 million square kilometers of sea ice in late September. And the motivation was basically there's been sort of huge spread in assessments of when that target could be reached. As recently as the last IPCC report, they basically suggested it was unlikely to happen before 2100 or so. And there have been a few scientists who've said it could be as early as 2015. So again, I don't have much time to go into this research, but basically we used two approaches. I'll just talk quickly about one. We looked at those 35 or so CMIP-5 models and looked at how well they did at two metrics: their climatology of September sea ice over that last 30-year period, and their trend in sea ice over that last 30-year period. And we kept those models that fell within 20% of the observations for both of those metrics. So here you have the observed average September sea ice extent for 1979 to 2010, and then each of these GCMs. And so we basically would retain any GCM that was in 20% of the observations. If we take that group and the union of that group and the group that had a sea ice extent within 20%, a sea ice extent trend within 20%, of the observations, and you end up with retaining 8 GCMs. And shown here is the average of the 8 GCMs that we retain for sea ice extent and for sea ice trend. So it's really a very simple approach. When we look at those 8 GCMs and then just sort of track them, and then the red line is going to be the average of the 8, at what point do you reach that threshold that we identified? Under RCP 8.5, you hit it in the mid-2050s. And interestingly, under RCP 4.5, which a lot of people would argue is maybe too rosy a scenario, you actually, in some of the models, never really do bottom out. You actually can sort of find a stable state at roughly that level. So again, these climate models seem to be underestimating the rate of sea ice loss. I think that causes us to need to be very skeptical about it, but still valuable, I think, to look at the model. So this model-based approach alone suggests the mid-2050s. My personal opinion is that it's likely to be a lot sooner than that, but that really is just an opinion. Okay, and then just a couple more minutes here to talk about some of the mid-latitude research that we've led, starting with our paper in PNUS in 2012. So there was this sort of pattern of like 3 or 4 winters in a row between 2007 and 2010 where there just seemed to be a lot of areas that had heavy snowfall throughout the northern hemisphere that got a lot of attention. Seeger et al. Reported a link to to the North Atlantic Oscillation, possibly having explanatory power for the U.S. and Northwest Europe. Also been some papers linking positive phase of ENSO to snowy winters. When you just take a very simple approach and just look, we were sort of motivated to look at those first 4 winters. So you see snow area across the northern hemisphere north of 35 for each of those 4 years. If you correlate, again, red being the snow extent for winter, 2007, 2008, 2009, 2010, there isn't a consistent relationship with the AO. Positive, AO and NAO, let's just treat as the same here, the blue and the green. In some years, positively correlated, some years negatively correlated. Same thing for ENSO. Some years negative, some years positive. This is actually just a couple of years, but it was the motivation to sort of look further at this. Whereas when we looked at the sea ice area for September through November, consistent negative correlation, although small in one case for those 4 years. So what would a possible mechanism be to link loss of sea ice in the Arctic to snowy winters and cold air outbreaks in the mid-latitudes? So the basic idea proposed in this mechanism is that when you lose sea ice in late summer and early fall, you can get profound temperature anomalies. In the past, that's the time of year when the sun disappears. If you essentially had almost a continental surface with extensive sea ice, temperatures would drop really quickly. When you have open water in late summer, you're having additional solar radiation, especially in July and August, still getting in and warming things. And then you're going to have that sort of persistence of that warmth. It's going to take time for the area to cool off again, as long as it takes essentially for things to refreeze. In some areas, temperatures are going to stay close to even freezing as you get into, say, October or so. So you have very large positive temperature anomalies. What does that mean? When you have that warm air, when you have that potential for moisture flux with an ice-free ocean, that brings surface a flux of heat and moisture into the atmosphere in late autumn, maybe into early winter. And what we propose is that could affect the winter atmospheric circulation. Just to quickly make the point that in 2007 we had, there was a big sea ice anomaly there. Lots of additional solar radiation came in, and anomalous temperatures of as much as 7 degrees Fahrenheit above normal in 2007. Okay, so when we regress, this is totally observations at this point. When we regressed the detrended autumn Arctic sea ice record, September through November, over that 31-year period, with the sea level pressure anomalies, this is the pattern we got. In some ways it looks like the negative AO, but not really. You see that it's got a less zonal structure. So again, just to sort of point, so the idea here is when you have a negative sea ice anomaly, you have higher pressure, anomalously high pressures over these areas, anomalously low pressures there. So in some ways like the negative AO, but not quite. That's the sort of typical negative AO phase. As you can see, a more zonal look. And actually their time series correlation is also fairly low between that detrended autumn sea ice area and the winter AO. So something else going on here. It's not the same as the AO. So then we regressed this fall Arctic sea ice area anomaly on snow cover December through February with units here of 1 million square kilometers. Smaller actually than some of the anomalies that were observed in sea ice extent for 2007 and certainly 2012. And a tendency for something like, and this is again over about 30 years of observed data, tendency for something like 15% more snow in these areas you see in red when you have that low sea ice extent. So we know clearly natural variability is large in these regions, but you can see the regression there. And then what happens if we look at the incidence of extreme cold events? Also a somewhat similar pattern. When you have that there's a regression again. When you have that low sea ice extent, a tendency for these cold air outbreaks, as much as a 50% increase in the frequency of these cold air outbreaks, especially over sort of eastern parts of the continents, but over a much broader area as well. So then we went to climate models and did an experiment where, using CAM 3.1, two different approaches. One, a control, basically using a sort of climatology, but seasonally varying of sea ice extent in the Arctic, and then a perturbation where we took out sort of characteristic ice loss in autumn and winter along the lines of what we've observed in some recent years. And when we difference those patterns, so these are the actual anomalies in the sea ice that we used in autumn and winter for the prescribed experiments. And if you look at what the models suggest, a pattern somewhat similar to the observations, when you have that lower sea ice in the Arctic in the models, you do see that overall feature of an anomalous high. Might actually look more like the AO, though, somewhat like the observed AO. And to some extent, you see as well in the temperature record, maybe a tendency for somewhat of this cold air outbreaks making their way in, although it doesn't look that much like the observations, but certainly it's not a zonal structure. And if we compare the observations for the regression with the snow cover that I showed earlier, you can make the case that there's some similarities in this modeled pattern. I wouldn't go too far with it. We can't really expect the models to get this right. But I think at the first order, you can make the case that in the model experiments, with this one model, some of the overall features were reproduced. Low sea ice cover being consistent with anomalously high snowfall over parts of the mid-latitudes, especially sort of eastern part of continents. So I think that I'd better wrap up there so we have some time for questions. I apologize for going a little long, probably quite a bit long. Something that we're in the process of writing up now. What happens if we focus on just the last 6 years when there's been this very strong negative sea ice anomaly, and compare that period? So not a regression over the full 30 years, but a differencing of these recent 6 years that had a lot less sea ice. Is that sort of a state change? And we haven't had a chance to compare this to the natural variability yet, but certainly a tendency for anomalous highs over the last 6 years in November, and anomalously easterly flow here. That paper in oceanography that I mentioned noted that this is the type of flow that can sort of help you get a Sandy type event. But again, one storm, you can't go too far with that, but it is interesting to see this based on just 6 years of observed data. So I think I'll close there. I apologize for running long.